So this video is going to cover an introduction to conservation of energy. And to introduce this topic, we are going to talk about a diver that falls off of a diving platform and lands in the water below. As the diver begins to fall, his kinetic energy increases because his velocity increases, and his potential energy decreases because his height above the water decreases as he falls. We can calculate all the diver's energy by simply adding his kinetic and potential energy together. We also know that since he falls, his kinetic energy comes at the expense of his potential energy, so no energy is added to the diver or taken away from the diver as he falls towards the water. This idea that no energy is lost or created when he is falling is called the conservation of energy, which means that the total energy is the same as the diver falls into the water. So let's look at this diver's situation a little bit closely. So if the diver has a mass of 80 kilograms, what is the diver's energy when he is standing on the 10-meter diving platform? So we know that the diver's total energy is going to equal kinetic energy plus potential energy, and kinetic energy is 1/2 mv squared, and potential energy is mgh. We know that when he is standing on the diving platform, he doesn't have a velocity, so his kinetic energy is 0, but he does have potential energy, which is equal to his mass times gravity times the height above the water, which is 10 meters. So we find that this total energy is 8,000 joules. Next, we could be asked to find the diver's height above the water when he is traveling 5 meters per second. We know that the energy of the diver is the same throughout his fall, so we can apply our energy equation to the situation. We know that the total energy is still 8,000 joules, and we know his mass is 80 kilograms and his velocity is 5 meters per second. So we plug in these values to our equation. We find the height above the water is 8.75 meters when he is traveling 5 meters per second. Next, we could be asked what the diver's velocity is when he reaches the water. So to set up this equation, we know that the energy is still constant, and the height is now 0 though, which means he will have 0 potential energy. We can solve then for the velocity, and we find that he would be moving 14 meters per second when he hits the water. So this basic idea of conservation of energy is that energy cannot be created or destroyed, but it can be converted into other kinds of energy. So there are a lot of different kinds of energies that we will use in this class. The first one is kinetic energy, which deals with energy associated with an object's speed and mass. So we've already talked about this at length. There's also potential energy, which deals with an object's position. There's gravitational, elastic, and electric potential energy that we've already discussed in the potential energy video. There is also internal energy, which can be associated with an object's motion or position of atoms and molecules. This can be thought of as thermal energy. So if the atoms are moving quickly, then there will be a higher temperature of the object. There's also sound energies, which deals with whenever we hear noises. And there's also radiant energy, which is the energy associated with light and other forms of the electromagnetic waves. And finally, there is chemical energy, which is the energy associated with the reactivity of chemical compounds. So this is like if you throw two reactive chemicals together and they blow up, that's chemical energy. So let's look at an example to see how these kinds of different energies can convert between one another. So we have a box that slides across a rough surface. So the conservation of energy tells us that the energy before an event happens will equal the energy after the event. And before the event, we just have the energy of the box moving along the surface, which is all kinetic energy. But when the box begins to move, it feels a friction force between the surface and the box, which converts in the mechanical energy or the kinetic energy into internal energy. And the box also makes noises as it moves across the floor. So we also know that there's a sound energy associated with the box's movement. So in the end, all the box's kinetic energy converts into sound and internal energy.